Section 21.8 Stereochemistry. Examining the configurations of the product of a ligand substitution reaction helps review the mechanism of the reaction. To be more specific, it helps review the structure of the intermediate. Let me give you one example. This Y is the entering ligand. It's about to replace this X ligand in this trans transition metal complex. In this trans transition metal complex, the metal is bonded to 4 L ligands, 1 A ligand, and 1 X ligand. A and X are in the trans positions. So now Y is about to replace X. The final product is Ml4AY plus X. Now let's examine the configuration of this product, Ml4AY. If A and Y are still in the trans positions 100%, then we know the intermediate structure is definitely a stable square pyramidal structure. But what if we see a very large percentage of this product are cis? So it's not only trans, but there are also cis configuration, and in particular, if we have a large percentage of cis, as large as 67%, then you may tell that the intermediate structure is very likely a trigonal pyramidal structure. Now let me explain with some pictures here. So over here, this is the transition metal complex with A and X in the trans positions. And then this X may leave the metal to form this square pyramidal structure. And Y attacks the metal on the opposite side of A. Okay? This is to minimize the steric effect. Of course, Y can attack the metal from here or from here, but from the opposite side of A, there's more space and less steric effect. That means lower energy barrier. That means this is faster. This is favored energetically. And then the product is 100% trans, or nearly 100% trans. A and Y are in the trans position. Now, what if the intermediate is a trigonal bipyramidal structure like this? So over here, you can see this is actually favored compared to this one, because VSEPR theory tells us you should separate those ligands as much as possible. So over here, this is 90 degrees, this is 90 degrees, but over here, there's 120 degrees. All right? Well, of course, if you look at the electron-electron repulsion between the d electrons and the electrons from the ligands, there's also ligand field stabilization energy you have to consider. So it's not always true this trigonal bipyramidal structure has lower energy than this structure. I'm just saying, well, this is possible. This is possible because if you look at the separation between these 3 ligands, 120 degrees, 120 degrees, 120 degrees. Over here, it's 90 degrees, 90 degrees. So just based on VSEPR, we say, well, this is possible. Okay, then what if this intermediate structure is trigonal bipyramidal? Then this Y can attack this metal. Okay, between these 2 ligands, or between these 2 ligands, or between these 2 gray spheres. If Y attacks the metal between these 2 gray spheres, okay, the final product is going to be trans. Okay? But what if this Y attacks the metal between this orange A and this gray? The final product will be cis, like this. this Y can also attack the metal between A, this orange A, and the other gray sphere here. It's still going to be a cis. All right. So if you look at the three different products, this one is trans. This is a cis. This is also a cis. Again, this green Y attacks the metal between this orange and this gray. This green Y attacks the metal between this A and the other gray. All right, so that's why you have two cis. Okay, I just want to remind you, these two are identical structures. They are not chiral. They are not enantiomers. They are identical structures because you can easily see there's a sigma symmetry plane that contains the 5 atoms in the middle. All right, and a sigma symmetry plane is considered the SI symmetry element. Oh, I'm sorry, S1 symmetry element. S1 means you rotate 360 degrees and followed by a reflection. It's equivalent to a sigma symmetry plane. And as long as a structure contains a S1, S2, S3, or any Sn symmetry element, this structure is achiral. So these two are achiral. They are not enantiomers. They are just identical structures. All right, so you can just imagine we can just rotate this 180 degrees and then rotate this a little bit, and then you'll see the red, the orange can superimpose this orange. At the same time, the green can be superimposed on this green. So these two are the same. At the end, you'll find 1/3 trans and 2/3 cis. If this orange sphere A has similar size as the gray spheres and also similar chemical properties as the 4 gray spheres, and then you have 1/3 of trans and 2/3 of cis. But of course, if this A is much more bulkier than the gray spheres, I would say, well, you probably will have more trans, because it's more likely for this green sphere to attack the metal between the two smaller gray spheres, and then you'll get more trans. You'll get more than 33% of trans.